Hello dear students. So, in today's class we will try to derive the vectorial form of the momentum equation. We have understood various different types of forces, how we can combine them on all that. So, this class is going to, before we move ahead to the scaling analysis, this class we will try to do two things actually. Number one, we will try to see what is the vectorial form of the momentum equation, right. So, we will try to see the vectorial form of the momentum equation. What does it mean? We will try to write the momentum equation for a velocity vector u, right. Now, that is the equation which is basically a vector equation. That means, the total derivative is operating on a vector. We have already seen how we can calculate the total derivative of a vector, right. We have also seen how we can account for the rate of change of unit vectors using the same derivation, right. We have seen all that. Now, let us try to put it together. We will try to see how we can put all those things together and write down the vectorial form of momentum equation. Then subsequently, once you have written the vectorial form, it becomes necessary for us to write the component equations. That is, write down the component equations from the first part, component equations in spherical polar coordinates. Right. So, we will try to derive the vectorial form of the momentum equation, and then we will try to split this equation into component equations. Component equation as in one equation for the things on x axis, one equation for the y axis, one equation for the z axis, three different equations. So, eventually these three component equations are the horizontal, vertical and the momentum equations that we will use later. Right. So, this will give us the three momentum equations. Right. So, let us now look at the vectorial form of the momentum equation. Now, when we are trying to write down or when we are trying to discuss about the momentum equation, we are basically trying to conserve the momentum, right. So, from the Newton's second law of motion, we know that the acceleration can simply be written as the sum of forces per unit mass, right. Now, if we apply this to an inertial frame of reference, a frame of reference which is either at rest or moving at a constant velocity. So, then we can write the acceleration, the vector as dA ua by dt. What is dA? dA is this total derivative is the inertial derivative. That means, it is operating with respect to a frame of reference which is at rest, right. So, this should also be equal to the sum of the forces, right. So, this is what I have been telling you since the lecture 1, that as long as the frame of reference is inertial, this equation should be sufficient. That means, you are in a position to apply the Newton's laws of motion as it is. So, the object's movement is according to the forces that you know and that you can write equations, right. But when the things become non-inertial, you have already learned that when the things become non-inertial, you may have to add additional forces which are nothing but the inertial reaction terms of the real forces. These forces were also called as the apparent forces or the pseudo forces, right. So, we have already seen that if we wish to apply this equation as it is to a non-inertial frame of reference, that is a rotating frame of reference in this context, then we need to add the apparent forces on the right hand side. So, this sum of forces must also include, let us say at this point itself, sum of forces must also include the apparent forces. This is the basic idea. Now, let us say ua is the velocity related to the inertial frame of reference. right. This derivative is with respect to the inertial frame of reference. Now, let us call UA, the velocity UA is the velocity which is relative or which is with respect to an inertial frame of reference. Right. So, let us say UA is the velocity related to the inertial frame of reference, and U without the suffix U is the velocity relative to a non-inertial frame of reference, to a non-inertial frame or rotating frame of reference. Now, in order to transform, so basically we have this equation, where acceleration is just the sum of forces. Now, let us call this equation as equation number 1. Now, in order to write equation number 1 for the non-inertial frame of reference, or we can also say that in order to transform this equation for a non-inertial frame of reference, we need to find the relationship between UA and U. So, this relation is to be known. What is the relation between UA and U? So, if an object is moving with respect to inertial frame of reference, if suddenly the frame of reference starts to accelerate or starts to rotate around itself, how will the velocity of the object with respect to a non-inertial frame of reference connect or transform to the velocity with respect to inertial frame of reference? That means, in order to write equation number 1 for a non-inertial frame of reference, we need to have a relation between, we need to know how UA can be transformed to U. How UA can be transformed to U. UA and you need to have a relation between UA and U. Now, we can arrive at the same result. Let us say we can arrive at the same result, as in we are basically trying to find out what is dAU by dt and what is du by dt. So, we can arrive at the same relation by using the relationship between, so u is a vector, right. So, we already have a relation by using a relation between dA. So, we have a relation something like that. The total inertial derivative of a vector is related, let us say we have a relation between dA A by dt and dA by dt. What is the difference? One is the total derivative in an inertial frame of reference of a vector. The other one is total derivative in a non-inertial frame of reference of the same vector. Right. So, which basically accounts for the acceleration of unit vectors. So, that is where when you talk about the non-inertial frame of reference, that is when you talk about the acceleration of the unit vectors. Right. So, what is the relation that we have here? So, how are these two quantities related? So, we know that dAA by dt is equals to dA by dt plus omega cross A. Now, what are we trying to do? We are trying to derive a relationship between, we are trying to see if we can write equation 1 for the non-inertial frame of reference as well. Then we thought if we want to write it, it is better we know a relation between the inertial velocity and the non-inertial velocity. Then we realized it is not something different than seeking a derivative with respect to both the frames of reference of the same vector. Right. So, then we have recalled this expression. Let us call this expression as equation number 2. What is this expression doing? This expression is connecting these two things. What are the two things? One, let us say if A is U, for example, if A is U, what are we trying to do? We are trying to write the acceleration with respect to an inertial frame of reference seems to be equal to the acceleration with respect to a non-inertial frame of reference plus an additional term. What is this additional term? This additional term is nothing but omega cross A. What is this additional term telling us? This additional term is telling us, is speaking about an effect which has come into existence only because of the omega. What is omega? Omega is the angular velocity. What is omega doing? angular velocity is making everything non-inertial. Had it not been omega, then had it been the case that omega is 0, then we can simply say that both the derivatives are equal. So, practically we can now replace A with u, the vector A with u, right. So, now let us say we use the position vector. We apply this relation for a position vector. So, how can you write dA r by dt is equals to dr by dt plus omega cross r. How can what we can write ua, the rate of change of position is the velocity, ua is u plus omega cross r, right. So, now I was telling that if we want to write equation 1, that is the acceleration as sum of forces per unit mass, this is now at this point of time you remember this very clearly, this is valid for an inertial reference frame. Now, the idea is to be able to write equation 1 for a non-inertial frame of reference as well. Then I said in order to do that we need to have a relation between ua and a. Now, using the vector derivative, we have seen that the velocity ua can be written in terms of u as, so now we have u plus omega cross r. Now, we have this relation established, right. So, this question mark, right, this question mark what you see is referring to this relation actually, right. Now, now ua is a vector, we can apply this relationship between the dA by dt and dA by dt to the vector velocity vector as well. If we do that, so we can, let us say we call this equation as, we can apply 2 for equation 3 as well, right. So, how will it look like? So, dA ua by dt is equals to dA ua by dt plus omega cross ua, right. Now, using from this using equation 3, in the above expression, we can write dA ua by dt is equals to d by dt of u plus omega cross r plus omega cross u plus omega cross r. So, I corrected a mistake that I have written dA dua by dt. So, now what I have done is wherever there is ua on the right hand side, I have simply written ua in terms of the inertial velocity plus the curl term, right. So, now let us see how we can expand this. So, this becomes du by dt plus d by dt of omega cross r plus omega cross u plus omega cross r, right. So, this becomes du by dt plus omega cross dr by dt So, now we have a vector triple product on the right hand side, and this is still dA ua by dt. Right. So, what I have done, I have taken this derivative inside the bracket, and I am under the assumption that the angular velocity will remain a constant with respect to time. So, that means, so I can take it inside, and then I have dr by dt, which is again anyway going to give back the velocity only, right. So, I can write dA ua by dt is du by dt plus omega cross u plus omega cross u plus omega cross r. Right. Now, we have this vector triple product, and then we have the similar terms omega cross u. Now, we can simply simplify this algebra, saying that which is equal to du by dt plus 2 times omega cross u plus right. Now, about this vector triple product, what I can write is omega cross r is simply, if it is the radial vector r, we can simply write it as, by using the vector identity, we can simply write it as minus omega square r. Using this, dA ua by dt is du by dt plus two omega cross u minus omega square r. Right. Now, we wanted to have a relation between the total derivative of velocity in the inertial frame of reference and velocity in the non-inertial frame of reference. Here we have the same. Right. Now, so using this Newton's second law of motion, we can see that this one dA ua by dt is equal to sum of all this. Right. So, now we have, let us call this equation as 4. What is this equation telling us? This equation is just giving us that if you take the acceleration with respect to an inertial frame of reference, it will be the sum of acceleration in a non-inertial frame of reference plus some other terms. Right. Now, if we bring the equation number 1, now let us talk about that equation number 1. What is it? It is dA ua by dt is sum of all forces per unit mass. Now, look at this equation number 1. It is just telling us the things with respect to an inertial frame of reference. We also said we can apply Newton's second law of motion as it is, as long as the frame of reference is inertial. But when it becomes non-inertial, we need to talk about the apparent forces, all those things. But at this point of time, I can simply write the sum of all forces as only the inertial forces as the PGF, the pressure gradient force, plus the gravity, right, plus what else? Any other, the third, the real force, the frictional force, right. If we substitute this equation 1 into equation 4, what we can write is this PGF plus gravity plus the frictional force is equal to du by dt minus omega square r plus 2 omega cross u. Right. So, rewrite this equation as du by dt is equals to the pressure gradient force plus the gravity plus the friction minus 2 omega cross u plus omega square r, right. What is the derivative that we have on the left hand side? On the left hand side we have the acceleration in a non-inertial frame of reference seems to be the sum of all these things. Now, the most interesting thing is that this has come by itself. Naturally, when you just use the vector transformation from inertial to non-inertial frame of reference and then you choose your vector to be the velocity, it comes out naturally that the apparent forces, they come naturally into the equation, right. So, this is the beauty of using this transformation, right. Now, you know all these forces very well, right. So, du, this PGF is the pressure gradient force, gravity, frictional force, and this is the Coriolis force and this is the centrifugal force, right. So, we can write, this is the vector form of the momentum equation. We started with, now we will also write this for completeness. We started with this equation which is the pressure gradient. Let us say this is, let us say minus 1 by rho del P plus the gravity plus the viscous force, right. So, this is the complete set of equation that we will require. What do you call this? This you call this as the vector form of the momentum equation. So, this is the familiar form anyway, right. So, this familiar form, let us say I write it So, I am not expanding the frictional term because it is too lengthy. Okay. So, I am just writing it as Fr. Right. So, what is this? This is the familiar momentum equation which represents the conservation of momentum in a rotating frame of reference. Now, what does it state? It states that the acceleration following the relative motion in a non-inertial frame of reference equals the sum of the Coriolis force, the frictional force, the centrifugal force, the gravitational force and the pressure gradient force, right. Right. Now, this is the most important equation in atmospheric dynamics. Okay. So, this is the first topic that we have to learn. Now, what we will do in the next class is that we will try to split this equation. Now, u is the velocity vector which has 3 components, I component, j component and k component. We will try to split this equation and write its u component, v component and w component separately. And we will take the help of the appropriate coordinate systems. Let us say if we will try to see whether the coordinate system is Cartesian or we have to resort to any other coordinate system, right.